Welcome back, 251ers. If you remember, hope you remember, Chapter 7 is where we're at. Bands that Professor Sylvan played with so long ago. This will show you how long ago it was. This is a shirt from, I don't know if you could read this, George seems to think you can. This is a shirt from a benefit that my band played after Hurricane Katrina, which we talked about way back in chapter, whatever chapter that was. When did we talk about Hurricane Katrina? Chapter 5. That was just the last chapter, or 6, I'm sorry. That was the last chapter. That was a long time ago. That's one of the shirts from. So no crazy music to play with it because it's from a show that my band played. But it was the one that I saw in my drawer, so I picked it up. Here we are. Surface. So the last lecture, you learned what a current is, if that was not something you really knew about. You learned that there are surface currents and deep currents. And you learned a little bit about how we measure said currents. So we're going to spend the rest of the chapter talking about the currents and defining them and discussing where they are and why that matters. So start off with the surface currents, which, not surprisingly, are at the surface. They occur above the picnic line. So basically from a depth of approximately 1 kilometer up. Although, I guess less than 1 kilometer. The picnic line, remember, there's all the different clines. The picnic line, what's picno? Density. Starts around 200-ish meters and goes down to about 1,000 meters. So this is really probably more like the upper few hundred meters. So surface currents, they're going to be driven by wind. Affects only about 10% of the volume of ocean water on Earth, right? Because it's at the surface, right? So it's only affecting things that are at the surface, so about 10% of the water on Earth. These surface currents develop due to friction between wind and the ocean surface. Basically, the wind is blowing, and the ocean surface is right there, and it's liquid, so the wind can move that ocean surface. When it blows on the surface, it creates friction, and it moves the water around. About 2% of wind energy is transferred to the ocean surface. What this means is that a 50-knot wind, 50 knots is 50 nautical miles per hour. Nautical miles are based on how long, I think it's a minute of latitude is, and as you know, latitude changes going north and south the length of latitude lines, so that it actually, a nautical mile can change slightly going north or south, but it's more or less about the length of a mile. So nautical mile, 1 knot is a nautical mile per hour, 1.85 kilometers per hour. But so 50 knots is more or less 50 miles per hour. So 50 mile per hour wind is a strong wind, right? Strong wind at sea as well. That will create a 1 knot current. Surface currents, therefore, are always slower than the speed of the corresponding winds that make them. I shouldn't even have to write that, to be honest, but there it is. Obviously, you can't transfer 100% of the energy from one medium, the air, to another, the water, especially because water is a lot heavier, a lot more dense than the air, so you wouldn't expect something that is pushing so much air that it can move 50 knots in the atmosphere to be able to do the same thing, the same amount of energy to do that to the oceans. It takes a lot more energy to move the ocean. So in surface currents, they generally follow the Earth's wind belt patterns, and this is because surface currents are primarily caused by the winds. Therefore, they're heavily influenced by where the prevailing winds are on a regular basis. So don't take my word for it. This figure from your book. Wind influences the currents, and so that you should know really 2 wind systems. You should know the westerlies and the trade winds. Westerlies are blowing towards the west. Isn't that the opposite of what I said winds do? Anyway, I said that the problem is that these atmospheric weirdos, they have it all backwards. So westerlies push from the west and they go to the east. It's a receipt in my pocket. I was wondering what I was feeling in my pocket. So, and they push low latitude water to the east low latitude, well, mid-latitude, I would say. And then the Coriolis pushes that to the right, which ends up in the northern hemisphere, comes up down here. On this, the westerlies are these ones right here, and they also end up going to, they go to the left because they're in the southern hemisphere. And the trade winds push low latitude, I'm sorry, yeah, this is a typo. The trade winds push low latitude waters to the west. You know what, I'm going to stop this right now and correct it so that that mistake doesn't make its way into your slides, which I have not yet printed. I apologize for that. Let's say mid. There you go. 251ers. It's okay to make mistakes. You've got to own up to them and correct them. Westerlies push mid-latitude water to the east. Trade winds push low-latitude water to the west. Low latitude on either side of the equator. I am really losing my mind. On either side of the equator, right? So basically below the tropics, you know, up to maybe 20-ish degrees north, up to maybe 20-ish degrees south. Don't quote me on those exact numbers, but those would be low latitudes. And they're pushing, trade winds are always pushing to the west. Trade winds are going to be really important. We're going to talk to them a lot. Basically, an absence of trade winds, which happens periodically, is what initiates in El Nino. So trade winds are pushing water that way. And so this essentially forms that side of what you're going to find out is something called ocean gyres. Right? And so something I should point out from this figure, so in green here we have the westerlies and the trade winds. The westerlies are in the darker green, the trade winds are in the lighter green on both sides of the equator. And then in blue, in this kind of lighter colored blue, we have the direction of the ocean currents in those same areas. So you can see that the combination basically of Coriolis and the prevailing winds over large areas is what causes large current patterns. So there's 4 different types broadly of surface currents. One are gyres, large circular loops of moving water. These can be anywhere. Specifically, subtropical gyres are centered around 30 degrees of latitude. There's 5 of them, and they're really big and they're really important. So we're going to talk about subtropical gyres in particular versus gyres and overall just circular pattern, circular current pattern, but the subtropical gyres very specifically are in the subtropical areas where the center basically of the circulating mass of water is about 30 degrees latitude. 30 degrees is subtropical. Tropical is 23 degrees or less, right? 23 and a half or less. Subtropical is just a little bit north or a little bit south of that. The equatorial countercurrents. This is eastward flow. Eastward being that way, if north is that way. Eastward flow between north and south equatorial currents. And this is because there is no Coriolis at the equator. Nope, no Coriolis at the equator. You remember this. You remember this from chapter 6. We're in chapter 7 now. So the reason that you have these equatorial countercurrents is because the trade winds just north and just south are blowing water to the west. And then at the equator where there are no trade winds and also no Coriolis, the water kind of flows back right along the equator. So and then finally we have the subpolar gyres, which rotate opposite the subtropical gyres, and these are smaller and fewer than subtropical gyres. Okay. I'm sorry, I'm staring at this though because this makes it, the way it's written here, it makes it look like gyre, that there's 4 types of surface currents. Really, there's 3. There's 2 specific types of gyres. I'm sorry, a gyre in general, I don't want this to be confusing for you. A gyre in general is a large circular loop. of moving water. And then the subtropical gyres center around 30 degrees, and the subpolar gyres are near the poles. And then we have the equatorial countercurrents. This is a map of the global currents. Ta-da! Showing you in red, we have some warm currents, and in blue, we have cold currents. The direction of those currents generally is in reference to the other side of the current, like here and here. But it's also showing you it's strongly influenced by basically where that water is coming from. So these California current, which is moving south, is considered a cold current, even though it's headed towards the equator, because it's bringing water from up here, which is kind of colder. And if you've ever been swimming in water on the West Coast, especially kind of Southern California area where the weather is warm all the time, so you expect the water, you run out there expecting the water to be warm, and much to your surprise, if you haven't been in that water before, it is not warm at all. And so that's because that water is coming from from up north, I should say. So and we can see the equatorial currents there. This is also a figure from your book. This is probably, as you're seeing it in the video, probably not super clear since there's a lot going on here. What I want to point out are the major current types in this figure. So we have our subtropical gyres. These are actually numbered in this particular figure. There's 5 of them. Remember I mentioned 5: North Pacific, South Pacific, North Atlantic, South Atlantic, and Indian subtropical gyres. And again, these big features are centered right around 30 degrees. North in that case, south in this case. You're going to learn that the western side of these subtropical currents have something called western boundary currents, which are thin, deep, and warm and fast. And the east side has eastern boundary currents, which are the opposite. They're fat and, I should say, wide, and they're a little bit shallow, and they tend to bring cold water with them. So, and then the shape of these things, basically big swirlies, is the same as the shapes of the subpolar gyres, which we have one there, and we have one there. And the biggest difference basically is the fact that the subpolar gyres tend to be smaller. There's a little one right here. And they're subpolar as opposed to subtropical. And then finally we have the equatorial countercurrent, which again, I told you, trade winds north and south of the equator are blowing water that way. And what happens is basically the water in the middle, water gets piled up over here, and then gravity brings it back, and the water in the middle where there's no Coriolis. No Coriolis means that the water can move kind of along a line of latitude instead of veering off one side or the other. And because gravity favors the water to move that way, because there's more water piled up over here from all the trade winds pushing water all the way across the ocean basin, the equatorial countercurrent goes right back pretty much along the equator where there's no Coriolis, and that's what that is. So this is a figure that doesn't look good on the board, but hopefully looks better on the handout. And what it's showing you is the relationship of the major wind patterns in the current systems. I've basically put them on top of each other. There were 2 figures in the book. One showed you the current patterns. This figure, actually, all these green arrows here, if you remember that, that's actually from the last chapter, the air-sea interactions. And that's showing you the the wind patterns, and they're basically on top of each other, not surprisingly. You can see here, like, there's these big high systems, right? High pressure systems. They're like right in the middle of the gyres. So it's kind of neat how you can see that, right? There and there. Those are all the highs. And all the lows along the equator correspond with the equatorial countercurrents and the equatorial doldrums. So, believe it or not, you know when I say this is going to be a short one? Oh, wow. That was a really short one. What I should have done was combine some of the previous video, which was a little bit long, with this video. But that was like one long topic, and I thought it was better to get through the end of that topic and then get on to this, which was really just an introduction to the types of currents. So since this was so short, I'll go back and review it really fast. Remember, surface currents made by wind, only Only about 2% of that wind is going to make it into the energy or speed of these currents. We have the westerlies pushing from the west to the east. That's how atmospheric scientists name their winds. So westerlies are pushing to the east, and that causes water to move in that direction. We have the trade winds, and the westerlies are in the mid-latitude. So they're basically what causes the northern in the northern hemisphere and southern hemisphere edges of the gyres, the subtropical gyres. And then we have the trade winds pushing things the other way, which form the northern and southern ends in their respective hemispheres of the subtropical gyres. So, and remember what a gyre is. The subtropical gyres in particular are really important, and then the equatorial countercurrents. And the subpolar gyres, it's not bad to know what those are. We'll talk about those less. In the next sections, we're going to start talking about subtropical gyres and get into them in a little bit more detail. So you know what? We're done. I'm going to leave it there. And when we come back, we'll talk about that. And I'll be wearing some shirt from some other band that you've never heard of, but that I used to play with. I'll see you then.